Hello, this is a video about kinematics, the kinematic equations, what they are, where they come from, and how to use them. So we know position, velocity, and acceleration. This is what we've been talking about. And these are all fundamentally related to positions in time. Position is clearly related to position. It's where you are. The velocity is how fast your position changes in a second. And then your acceleration is how fast the velocity changes in a second. Now, these are both related to how far you go in 1 second. So they're all related to each other in some mysterious way. We express these relations in the kinematic equations. They give us these relations in a way that are useful so that we can solve problems. So here they are, 4 kinematic equations. Maybe you notice some symbols in here that you haven't seen before, so let me explain them real quick. Delta x symbolizes the change in position. We use x because right now we're doing one-dimensional motion, but eventually we're going to have to deal with two-dimensional motion, and that has an x and a y. That's one of the reasons why we use it. Vi is the initial velocity. This I down here stands for initial velocity, because when we have accelerated motion, the velocity changes. Vf is similarly the final velocity. A is acceleration, and t is time. Now, if you don't know what number is associated with what variable, you look at the units. The units tell you. Meters is going to be a position. Meters per second is going to be one of these, a velocity. It should be meters per second squared. If you see meters per second squared, then it's an acceleration. I'm an idiot. Anyway, and then t is time. So here's why we have 4 equations. We have 5 symbols, right? Delta x, vi, vf, a, and t. This is sort of looking forward to how we're going to use them too. Notice that this one is missing a delta x. Delta x doesn't appear anywhere in here. A is nowhere in this equation. V final is nowhere in here, and similarly, time is nowhere in here. We have one equation for each missing symbol. And you might say to yourself, wait a minute, where's the one that's missing the initial velocity? And there totally is one. It's this, delta x equals vft minus 1/2 at squared, but it's not as helpful, so I'm not going to make you learn it. This is how you use the equation. So the hardest part of this is figuring out which equation to use for the problem, because I do not tell you. You list everything the problem gives you. You look for the equation that has all of those variables and nothing else. And then that is what you use to plug in the numbers and solve. How do you know what a number is supposed to be? You look at the units. Meters is going to be a displacement. Meters per second is going to be a velocity. Meters per second squared is going to be an acceleration. And seconds is going to be a time. So I will show you basically how you do this. You do not have skeleton problems. You have word problems in real life. But let's say Vi is 25. A is 75 or 7.5, and then t is 8. How do you find the final velocity? Well, you need an equation that has Vi, A, t, and then it also has to have Vf. So maybe you're noticing that the one thing that we do not have right here is delta x. It's nowhere up here. It's not even what I want to find. So the equation I use is the equation that does not have delta x, which is this one. You plug in the numbers and you get 85. I'm not going to solve that. There's an algebra video earlier in the playlist. So here, the way I figure out which equation to use is I say, okay, look, I have a Vi, I have A, I have T, I need delta X. So the one variable missing is going to be Vf, right? I don't have that anywhere. It's not what I'm looking for, and it's not what I have. So I do not need it in my equation. I look for the equation that's missing Vf, and it is this one. So that's what I use. Plug in the numbers, solve. Here, I have Vi, Vf, t, and I need delta x. So, Vi, Vf, t, is delta x. The one thing that is not anywhere in here is acceleration. So I don't need a in my equation. So this is the equation I choose. I plug in the numbers and I solve. And I get 180. Maybe try that for yourself if you want. So word problems are where you're going to see this mostly. And 2 really short notes. From rest means that the initial velocity is 0, because you start off resting, not moving. And if there's only one listed velocity, it's normally going to be the initial velocity. Not always. So, this is the kind of garbage word problem you're going to get. They will normally tell you a story about a deer or a person who is angry or scared, and they're running away. This is a lot harder to figure out what goes where, because it's not a simple, pristine math problem. But what you do is you look at the units. Meters per second squared, meters, meters per second. And you say, okay, these units will tell me what I have. This is an acceleration, because meters per second squared, so that's what I have. Similarly, that, meters, that means it's a displacement. Down here, meters per second, that's a velocity. Well, is it initial or final? And you look, it says final velocity, so this is the final velocity. Then what was the initial velocity? That's what you want to find. So you need the equation that has a, delta x, vf, and vi. Here it is. You notice that we're missing something. We are missing the time. That's okay. There's no time in here, right? It does not tell me the time, and it does not ask me to find the time. That's why I use this equation. Here, we have an airplane accelerating down a runway. So from rest, like I said, that's one of those phrases. It means that it does not start moving. Here, this number, the unit is meters per second squared, so that means it's an acceleration. Seconds, that means that this number is a time. And it wants me to find the distance. So I need the distance in my equation. My equation must have vi, a, delta x, and t. So I use this one, which does not have vf. I plug in the numbers and I solve. Here, a car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Find the acceleration. So, seconds lets you know that this is a time. From rest lets you know that vi is 0. Distance, 110 meters. That's a delta x because meters. And acceleration is what you need. So there we go. Vi, time, delta x, and acceleration is what I need. So my formula must have vi, t, delta x, and a. What I do not need is vf. I don't need that. So I use the formula with no vf. And this is the correct kinematic formula. Plug in the numbers, and you get the answer. These equations do make sense. You can stop this video right now if you want. This is not necessary, but these are not just garbage equations. They do, if you think about them, correspond to your intuitions about the world. This first one. So you know acceleration is the change of velocity with respect to time. So if you plug that in for acceleration, this is what you get. Now these times cancel, right? Divided by time, times time. So you get the final velocity is the initial velocity plus the change. Hey, makes sense. So right here, distance is equal to this garbage times time. Well, you know the average of two numbers is the first plus the second over 2. So the average velocity is the final velocity plus the initial velocity over 2, right? So what you have here is this equation. Delta x equals the average velocity times time. How far you go is, on average, how fast you go times the time. Down here, this one requires a little bit more thought, but it is still intuitive. Think of the acceleration if you start from rest. Your final velocity is acceleration times time, right? Your average velocity is going to be final plus initial over 2, which is your velocity at the end, right? Plus your velocity at the beginning, divided by 2, which is 1/2 at. That's your average velocity. So your distance is going to be the average velocity times the time. So 1/2 at, average velocity, times time. And maybe you notice t times t is t squared. So that's 1/2 at squared. This right here, how far you go is your initial velocity times the time. That is hopefully intuitive. Makes sense to you. So basically what you get is the distance from your starting velocity plus the extra distance you pick up from the acceleration, which is the average velocity of the acceleration times the time. And then this one, this is just garbage. It just comes out of the math. You have these equations, and then you can Frankenstein them together to get this one. There probably is an intuitive explanation. I'm just not smart enough to figure it out. Hope that was helpful.